Hey. So first let us recall what we discussed in the last class. We discussed about curves, simple curves on a complex plane. We say a curve is a simple curve when it doesn't intersect itself. We can call it as a simple curve or a Jordan arc. And we see what is a simple closed curve or a Jordan curve. So which is a closed one and which doesn't intersect itself. And we saw some examples here. And then I defined what is a winding number of a closed curve. It means how many circulations it took. That's what we call winding number. And then we saw formula for length of an arc, and we saw how to define a unit tangent vector. Then we saw what is a smooth curve. When do you say a complex curve is smooth? And then we saw what are contours. Contour is nothing but a piecewise smooth arc. It means it need not be smooth totally, but you can have some pieces. Each piece is smooth and they were connected end to end. That's what a contour is. And if you take a closed contour, you can say that is a closed curve which is piecewise smooth. That you can see. That is a closed contour. And we saw some examples here. Then we discussed maximum value of an integral along the given curve. For example, if you look at this integral, we observe that the maximum value is going to be the maximum possible value of the integral is going to be 3 root 3 pi by 8. And how we get this result? So we developed some inequality here, and this is what we call ML inequality. Why? Because once if you know what is the maximum value of the function on the curve, and you know the arc length L, then you can say absolute value of this integral is always less than or equal to m times L. That is maximum value of the function times L. Remember, we are saying it's not the global maximum of the function. On that curve, this is the maximum value that our function takes. Okay, so be careful. Yeah, and we did some problems and I gave you some work. I hope you have done it. And next, immediately we have seen Cauchy-Gauchard theorem. What it says, when you have an analytic function, and let's assume that the function is analytic on the given curve and also the interior of the curve, then you can say that integral of that function along that curve will be 0. Why? Because since you are taking a closed curve, when f is analytic, this integral is independent of path. When it is independent of path, it depends on only the starting point and the ending point. You know, starting point and ending point of a closed curve both are equal. Therefore, this integral value will become 0. So we saw some examples. When you take this curve mod z equal to 1, and we see whether this function is analytic on the curve and also inside the curve or not. So if you observe that, yes, the only problematic points for this function are plus or minus 2, but which are anyway not in the domain, like not in this circle. So therefore, you can conclude that the value of this integral is 0. And then we have seen and this is another question where the given function is not analytic inside this region. Why? Because the problematic points are -2 and +2. They are inside this curve. Now we need to see how to answer this question. Today we are going to answer this question. Okay, and I asked you to solve this problem. I think we did, because since it is analytic, we can directly substitute. We can directly integrate and substitute upper limit and lower limits here. That's what you can do. Okay. And if you look at the Cauchy-Gauchard theorem, where was it? Okay, let me. So we saw what is a Cauchy-Gauchard theorem. Let me present it here. Yeah. So this is the Cauchy-Gauchard theorem. When f is analytic at all points interior to and on a simple closed contour, then you can say this integral is 0. Means you have a curve like this. This is the curve C. And of course, if they do not mention the direction, we take anti-clockwise direction. So when you know f is analytic inside and on the curve, this integral value is 0. That's all. Now, but when you take a closed contours, but sometimes you may have a region like this. Let us say you have some region, you have some curve here C, and they gave one more curve here. Let me say C1 and C2. Now my entire curve is this. My curve is nothing but C1 union C2. This is okay. So now for this problem, how to solve it? So now if you observe that this region is not simply connected. Why? Because it's not simply connected. If we say a domain is a simply connected domain, if it looks like this, I mean, you give me any 2 points, you can happily join them. Like there are no gaps. Simply speaking, there are no holes for the given domain. Like if you take a disk, if there are no holes, then we say that that's a simply connected. But if you take a CD disk, which is not a simply connected one. Why? Because it has a hole, right? So I hope you understand what is a simply connected domain. Now we need to discuss the theorem for simply connected domain and multiply connected domain. So what is multiply connected domain? This is an example of a multiply connected domain. It means you're not actually including the region inside these circles, or not the circles, let's say these shapes. You're not including this part, you're only including the other one. Okay. Now let us see what is the theorem for the simply connected domains and as well as the multiply connected domains. Okay. So this is the theorem for simply connected domain. Let me be specific. So you can see that these two are same. There is no much difference between them when you have a simply connected domain. Now let us see an interesting theorem for multiply connected domain. And here is the theorem. So you try to understand what it says. Suppose C is a simple closed contour which is described in the counterclockwise direction. And let me show you a picture for better understanding. So this is the picture for multiply connected domain. Okay. So you have a simple closed contour which is here. This is the simple closed contour and which is oriented in counterclockwise direction. And now inside it you have subcurves, and each curve is going to be a simple closed contour, right? And which is totally interior to C. For example, you see C1 is interior to C and C2 is interior to C, right? And here C is traversed in anti-clockwise direction, whereas the CIs are traversed in clockwise direction. Like if you have a curve here, outside curve orientation will take it this way, whereas inside curve orientation will take it in the opposite direction, right? And here we have an assumption. Assumption is that so those interiors are not going to have any common points and they are totally disjoints. That is how we are going to assume. That means there is no intersection of those curves. Okay. So with that assumption, what we can say is that you take integration along this curve and this will be equal to, actually this one can be written like this: integral along C f of z into dz. This will be equal to minus of integral along C1 f of z into dz, okay, and minus of integral along C2 f of z into dz, and so on. Like how if you have n number of curves inside, then you are going to write all n number of curves. It means it says that integration along this curve, which will be same as integration along the inside curves. Like if you take it in clockwise direction, you're going to get minus, whereas if you follow the anti-clockwise direction, which will give you the plus. Okay. So this is what the theorem for multiply connected domains. But here you should understand one thing: f must be analytic on all of these contours and also throughout this multiply connected domain. If you ask me what is the multiply connected domain here, so this is the multiply connected domain. and I'm not worrying about the points which lies inside C1 and C2. We really do not worry about this part, the region inside C1 and the region inside C2. We'll just take care of the multiply connected domain. That's it. Okay, once if you know the function is integral over that, then I can say this entire integral will be equal to minus of sum of the integrals over these curves. Okay, so this is the theorem for multiply connected domains. But here you should know one thing, like what will be the value along this curve, that you should know. Okay, now let us discuss Cauchy integral formula, which is very important. And what it says is this: when you have some closed contour like this, let's say C is a closed contour, and you have a function f of z, and you would like to integrate this function, integrate this function along this curve, but you came to know that there is some singularity on this curve. Okay, singularity, I mean a point where f is not analytic. Okay, so at z0 you came to know that this function f of z is not analytic. Okay, if you see that it is not analytic at z0, it means we can see that this f of z may be in this form. F of z may be like some function, some nice function divided by z minus z0. You can think this way. Why? Because you are saying it is not analytic at z0. Then you can think that the given function may be in this form, g of z by f of z minus z0. And let us assume one thing. Let us assume that here g of z is not equal to 0. Let's assume that. Okay. So it means z minus z0 is not a factor of z of z. So now the question is this. Now the same problem can be rewritten like this. Suppose if you have integral along C, integral along a closed curve, like f of z by z minus z0 into dz. If you have it, what will be its value? So we can clearly see that this entire function has a problem at z equal to z0. Why? Because at z equal to z0 it is not analytic. And we know one more thing, the one more information is this function f of z is analytic on C and interior to C. Okay, so now Cauchy integral formula says this: the value of this integral will be equal to, this integral value will be 2 pi I into f of z0. Okay, so the value of this integral will be 2 pi I into f of z0. But here you should make sure one thing that is, this z0 lies inside this curve. Okay, and if you give importance for the number of rotations it is taking, like number of times this curve is rotated around this point, let's say if it is rotated 2 times, maybe we may multiply with 2. If it is rotated for 3 times, we will multiply with 3. Or what you can do is you can simply write a winding number. So this times of a winding number. This winding number will tell you that the number of times this curve is traversed around that point. Okay. So this is what actually Cauchy integral formula says. And let us see its statement. Yeah. So here is the Cauchy integral formula. Let f be a analytic function everywhere on the curve and also inside the curve. Then the value of this integral, that is integral along C f of z by z minus z0 into dz, which will be equal to 2 pi I into f of z. The same formula you can rewrite it like this: integral along C f of z by z minus z0 into dz, which is same as 2 pi I into f of z0. Okay, here I'd like to mention the winding number as well, where into eta, where this eta is the winding number. Okay, to understand this, let's do one thing. Let's look at a problem. Let's solve a problem so that we'll get an idea. The first question is this: what is integral along C? 1 by z minus 1 into dz, where C is this curve, where C is mod z equal to 2. Okay. So you can see what is the given curve, which is mod z equal to 2. It is nothing but a circle centered at origin with radius 2. Now you know where is this point z equal to 1. See, in place of z minus z naught, I have 1. So 1 is here. This is inside this closed curve. Yes, and we want that. So we are taking this z naught be any point interior to C. Okay. So now this 1 is a point interior to the given curve. Now it is in this form. This integral is looking like this. Integral f of z by z minus z naught into dz. And we observed one thing, z naught belongs to C, or inside C. And here we know what is f of z. F of z is nothing but 1. And whereas z naught is 1. So this implies you can see what is f of 1. F of 1 is nothing but 1. So using that, using Cauchy integral formula, you can say this is 2 pi I into f of 1. So which is nothing but 2 pi I. So therefore, value of this integral, that is integral along C, 1 by z minus 1 into dz. Okay, integral along C, where C is nothing but mod z equal to 2. This is equal to 2 pi I. So this is the answer. So it is very simple. You are simply using this formula, that's it. Now let us solve one more problem to get more clarity. So the next question, integral you are given with z into e power z by z square plus 1 into dz, where my curve is this z minus 1 equal to 1. So this is my curve. So you need to integrate this function along this curve. So can you apply Cauchy integral formula here? Come again.
E power z is a function which is analytic anywhere, sir.
Is that enough to say that we can apply in Cauchy integral formula here? First of all, it should be in this form, right? It should look like this: integral f of z by z minus z naught into dz. This is how it should look like, and you should recognize this z naught to be a point inside this curve. Like whatever curve you have it here, see, this z naught should lie inside to it. But first of all, like do we have any problem at any point here?
Yes, sir.
Okay, what are the problematic points?
The denominator becomes 0, sir.
What?
If z is equal to I, the numerator will become 0, sir. It is not defined.
Yeah, that's correct. So the problematic points are z square plus 1 equal to 0. So it means z square equal to minus 1. It means z equal to plus or minus I. So these are the problematic points. So first let me see the given curve. The given curve is mod z minus 1 equal to 1. It means it is a circle centered at 1 with radius 1. So since its radius is 1, let me go 1 unit from here and 1 unit from here. This is not looking like a circle, but assume this is a circle. Okay, I hope this looks like. Now you look at this circle. The problematic points are, one is I, minus I, and the other one is plus I. These are the problematic points. Whereas our given curve is this. This is what C. C is a circle centered at 1. Now, do you have any issue with this function inside this curve and also on the curve? Do we have any problem?
No, sir.
Yeah, we don't have any problem here. Then, can I apply Cauchy-Rorschach theorem? What Cauchy-Rorschach theorem says?
If a function is analytic inside.
Yeah, if a function is
Close the
analytic
contour,
interior to C and also on the C, then integral of that function is going to be 0. So this is what Cauchy-Gaussian theorem, right? Now using this theorem, I can conclude that value of this integral is 0. You can write a note using Cauchy-Gaussian theorem. Okay. Now let me do one thing. Let me give you a curve in such a way that at least one of these problematic points will come inside the curve. So if the problematic point comes inside the curve, then definitely you can apply that Cauchy integral formula there, knowing that the numerator function is analytic. Okay, so let me create one more question. Now this time the question is integral along mod z minus I equal to 1. The same function I will give, z into e power z by z square plus 1 into dz. So what is the value of this integral? Think. Again, do that analysis. Whatever analysis we have done for the earlier problem, do that analysis and see whether to apply Cauchy-Gaussian theorem or Cauchy integral formula. What do you think? Which one do you apply?
Cauchy integral formulas.
Cauchy integral formula. Why? Because if you look at the problematic points plus or minus I think I comes inside the curve. So the given function is not totally analytic on the curve and also interior to the curve. So first you plot the point, you plot the curve. So it is centered at I and its radius is 1. One more. Oh, it looks like an ellipse. Still it is bad, but somewhat okay, fine. Now let me assume this is I. Okay, and minus I will be here. So now this is what your curve, mod z minus I, which is equal to 1. So this is the curve C. Okay, so first let me do one thing. Let me write this guy in this form. That is what integral along C f of z by z minus z naught into dz. I need to write it in this form. But in the denominator, if you see, you have z square plus 1. But we know one thing. This z square plus 1 can be written as z minus I into z plus I. So you keep the problematic point in the denominator and you take the rest to the numerator. This one can be rewritten like this: integral along C z into e power z by z square plus 1 into dz, which can be rewritten as integral along C like 1 divided by z minus I into, can I write it like this, z into e power z by z plus I into dz. Okay, so now if you take f of z to be this, so if I take f of z equal to like z into e power z by z plus I, now this integral will get this form, integral along C. Now this entire expression becomes f of z divided by z minus I into dz. So using Cauchy integral formula, we know since I lies inside this curve, we know that answer to this problem is 2 pi I times f of I. Why? Because the problematic point is z naught, where z naught is I. But you know what is f of z? F of z is nothing but this. So you substitute I in place of z. So the final answer is 2 pi I into, this is I times e power I by I plus I. Okay, you can cancel, here you'll get 2i and you can cancel I and I. So the final answer is 2 pi into e power I. Oh, you'll have one more I. So 2 pi I into e power I by 2. Okay, 2 gets cancelled. So pi I into e power I, that is the answer. So answer to our problem is this, pi I into e power I. And let us try to solve one more problem. The next question, integral along C, this time z square plus 3z plus 1 by, now let me take 2 and 3. So if I take 2 and 3, z square minus 5z plus 6 into dz equal to what? So the first problem is this, where C is the curve, which is mod z minus, or let me take mod z equal to, so I want 2, so 3, not 3, 5 by 2. So this is the first one, and the second one you need to integrate along C, where C is given like this, mod z equal to, not mod z minus 3, which is equal to 1 by 2. And there is one more, the third problem is C, that is mod z equal to 5. Okay, so let us try to see how to answer this problem on these three curves. So first you work out, first you do some work and let me know what are the answers. I hope the first one is easy. So first you try to factorize the denominator. First of all, you see where the denominator is getting 0. Let me see it. Given that z square minus 5z plus 6, we need to see where it is 0. First let me write it as factors. This one can be written as z minus 2 into z minus 3, isn't it? So we know the denominator gets 0 when z equal to 2 and z equal to 3. So these are the problematic points. The denominator is going to get 0 here. So here first let me draw the given curve. So let me do the first one. So the first one is, so this is a circle centered at origin with radius 5 by 2. 5 by 2 it means it is 2.5. Let me say this is 1 and 2 and 3, 2.5 it means somewhere here, right? So now you need to draw a circle. Instead of a circle I got an apple here, right? So this is the circle and it is the point z equal to 3, and here is the point 2. So now if you look at the first curve, let me call it as C1, only one problematic point is coming inside. Okay, so we'll try to have this in the denominator, and the rest we'll treat it as f of z. So now you take the problem. So that is integral along C, which is what, mod z equal to 5. So mod z equal to 5 by 2. So this is nothing but z square plus 3z plus 1 by, and the denominator can be expressed as z minus 2 into z minus 3. So only 2 is lying inside. So what I'll do is I'll do it like this, mod z equal to 5 by 2. You can write it like this, right? 1 by z minus 2 into the rest, you can take it as f of z, or in other words you can write it this way as well, z square plus 3z plus 1 whole divided by z minus 3, and this divided by z minus 2 into dz. Okay, or if you feel it difficult, you do one thing, first you write 1 by z minus 2 and the rest you write it later on. So now the rest will become our f of z. So now it is in this form, f of z by z minus z naught. So since it is in this form, I'll compare with it. So what is f of z here? So f of z is nothing but z square plus 3z plus 1 by z minus 3. So now therefore, and let me see what is f of 2 here. F of 2 is nothing but 2 square plus 6 plus 1 by 2 minus 3. Yeah, you know this is 11 by minus 1, so this will be minus 11. Therefore, answer to this problem, I mean this will be equal to 2 pi I into f of z naught. F of z naught is nothing but 2. Therefore, the final answer is going to be 2 pi I into minus 11. Therefore, minus 22 pi I. This is the answer. Okay, so this is the answer for the first one, the first curve. Now you think about the second problem. Now if you look at the second one, you can directly see mod z minus 3 equal to 1 by 2. So it means it is a circle centered at 3 with radius 1 by 2. So the radius is 1 by 2, so this is what you'll have. This is what the second curve. Just to identify, let me name it as C2.